Hello everyone, welcome to the channel. In today's video, our main agenda is to model the time series of 10-year Treasury, and we're also going to forecast the yield for several days ahead. Let's get started. The models we're going to use in today's video are the third-order polynomial TLM and ARMA model in TLM. We're also going to include a seasonal component in it, but we will see that it's not really beneficial for our purpose. Now let's dive into the first model, which is the third-order polynomial TLM. First, let's denote the bond yield as y, and we model y at time t as the level, so mu is the level here, plus some error, nu t. Notice the indices t here. It means that we allow the level and the error to change over time. Now we can model this. We can model the level in the next equation. The next equation models mu t, which is the level at time t, as the previous level plus some growth at time t, plus some error term. The error term is for the level, and we are denoting the growth as beta. Again, the growth can change over time, and so we want to model that as well. We will model it in the next equation as the previous growth plus some change in growth, gamma, plus some error. So you see the pattern here. Every time we introduce a new variable, that variable will be modeled in the next equation. Lastly, we model the gamma t, the change in growth, as the previous change plus an error term. Now, DLM looks at a time series in two hierarchies. The first one is the observational, and the second one is the system level. The observational level is what we observe. So it is represented by an observational equation, which is the first equation here. And then for the rest, three equations, they lie in the system level. In the system level, we can see that we have three equations and three variables. Maybe this is why it's called the third-order polynomial TLM. I'm not really sure though, because none of the books that I've read mentioned this, even though it's very likely. And if you wonder why we model every variable, part of this, I guess, because TLM is based on Bayesian statistics. In Bayesian statistics, we always want to quantify our uncertainty. And so this is why we want to model everything in a hierarchical fashion. Okay, this is the mathematical representation. Now I want to show you the DLM representation. The DLM representation is more concise because we actually have only two equations. The first one is the observational equation, and the second one is the system equation, or sometimes we call it as the evolution equation. Notice that the error here for the observational equation is still the same, which is the nu t. And so is the system error. It's still omega, even though we only have one omega now instead of three, like in the mathematical representation. Now, theta is called the state vector. Theta is a vector of length 3. It contains all the variables. So the theta t would be the level, the growth, and the change of growth. Mu t, beta t, and gamma t. Ft is also a vector. So the apostrophe here means that the f is transposed. Okay. And by the way, f is also a vector of length 3. The first element is 1 and the rest are 0. And then G here is a known system matrix. And then nu here. Nu is assumed to be normally distributed with mean 0 and variance V. The omega, or maybe I should say nu t here, sorry. Okay. Omega t is also normally distributed. That's the assumption with mean 0 and variance W. Now, V here is only a number in this case because we are dealing with a univariate DLM, a univariate time series. While for W is a matrix, a 3 by 3 matrix. And the diagonal are, well, these 3 omegas here will be put in the diagonal of W. So omega of mu, and then omega of beta here, and omega of gamma. And the rest elements are 0. Okay, now the last equation here, well, it's not an equation actually. This is an initial information. So in DLM, when you fit a model, you will be iterating the process at each time step. To get the iteration going, you need an initial information, right? So that's why we have a theta 0 given the set of information at time 0. That is normally distributed with mean M0 and variance C0. When we apply this in R, M and C, you will see both of them. Oh, actually, only the M. You will see only the M0 in R. Actually, you will see the C as well, but I will set them to the default value, so yeah. It is saying that what is the state vector here at time 0, at the beginning, before the iteration begins. So what is the initial level, what is the initial growth, and what is the initial change of growth? One more thing about DLM, the third order polynomial DLM here is that V and W earlier are assumed to be independent, both internally and mutually. So what I mean by internally is that the sequence V has no autocorrelation, so that VT and Vs, given that T and S are a different time index, Vt and Vs would be independent, and so does W. And then what I mean by mutually is that it's not cross-correlated. Okay, now let's move on to the second model, which is ARMA model in DLM. ARMA is the short of autoregressive and moving average. Again, let's denote the bond yield as Y, and we want to model YT, but this time YT is determined by a new variable, which is X. XT is modeled as the linear combination of some previous values of X. Let's say that we have P previous values, plus a linear combination of several previous innovations. Let's say that we want to take Q several innovations. Innovation is another name of error. And then lastly, we add the error or the innovation at the time t. So the first term here represents the AR part, or more precisely ARP. So P is the order of autoregressive model. And then the second and the third terms represent the MA model. more accurately, MAQ. So yeah, like this. Now the dimension of this model depends on P and Q. Suppose we have denoted dimension as n. The dimension of ARMA model n would be a maximum value between P and Q plus 1. This is the mathematical representation of ARMA model in DLM. Now let's move on to the DLM representation. The DLM representation looks really similar. In fact, it is exactly the same as the DLM representation in the previous model, including the initial information as well. I'm not writing it here because it is the same. One thing I haven't told you is that the DLM representation has another alternative, which is a quadruple of F, G, V, and W. This is also true for the DLM representation in the previous model. Anyway, back to this. Even though the DLM representation is exactly the same, the definition is slightly different because we are dealing with ARMA model now. So F is still a vector of length n, but now n depends on the maximum value between P and Q plus 1. And then the first element is still 1, and the rest of the elements, so n minus 1 elements would be 0. And then for the G matrix, now it contains AR coefficients. So in the first column, we have 1, and then AR coefficients. So phi 1 up until phi p. And the rest of the columns are like the identity matrix, but you erase the last column. So 1, 0 until here, and then 0, 1, and another zeros, like that. Nu t is still assumed to be normally distributed with mean 0 and variance v, and v is still a number. Now the state vector is also a vector of length 3. Oh, sorry, not length 3, but length n. And the first element is the current observation of x, so xt, and then for the rest of the elements, this vertical line here is to saying that it keeps going 0, okay? So the only non-zero elements is the first element. All right, and then about the omega t is also assumed to be normally distributed with mean 0 and variance w. And now the definition of w is slightly different from the previous model. The w is a symmetric matrix now. The first one is 1, and then we have an MA coefficients, so psi 1 until psi q. And that's the same for the row. And then for the diagonal, you have psi r squared. R going from 0, R is going from 1 until q. So in column 2, row 2, column 2, we have psi 1 squared. And in the last row and last column, we have psi q squared. What about in the second row and qth column? The second row, we have psi 1, and in the qth column, the last column, we have psi q. So that element would be psi 1 times psi q. I'm saying that the state vector would be like this because we will be only doing the MA model. We will apply the AR model. So yeah, actually what we're going to do is applying purely MA model or moving average model. Now we are in our R Studio to apply the models that we've just learned. Before applying the models though, I want to show you and talk just briefly about the time series itself. Firstly, I load the packages. We are using the package DLM for implementing the nonlinear model. And then load the data and do some pre-processing. So the data set is from 2018 to 2023. Oops, sorry. But we will see that the 2023 data set is not of one full year because, I downloaded when the last data is on August 18th, 2023. This is the time plot. I've segmented the time series based on based on the year. So the leftmost part here is the bond yield for 2018, and then 2019, 2020, 2021, 2022, and 2023. We can see that the bond yield were at its lowest level in 2020, when the pandemic starts. And we can see that around early 2020 here, the bond yield plummeted to around 0.5. And then the bond yield level in 2023 is the highest. And by the way, while the level for 2020 is the lowest, at least for this dataset in the span of 6 years, the level at 2023 is the highest in the span of 10 years. Looking at a glance, we see that it's quite similar to a quadratic equation graph. So that's why I decided to try to fit the model using the third order polynomial DLM. Maybe some of you think that it is more suitable if we fit a second order, which is a linear growth. We can certainly do that too, but I just want to show you that we can use the quadratic growth to model this time series. These are some helper functions that I made. Now, I want to build up the modeling. Firstly, I'm going to use the polynomial model only. So the third order polynomial model, we can use the function TLM mod poly to build the model object. And the 3 here is the order. So the complete code would be order equal 3. Okay, and this is the M0 that I was talking about in the initial condition earlier. I set 2.5 here because that's around the level initially, 2.5. So by setting this, I'm saying that my initial belief of the level is 2.5, and then my initial belief for both the growth and the change of growth are 0. And then dv is 5, so the observational error, the error for the observational error term has a variance of 5. And then for the w, we only step the diagonal part only. So 10 is the omega for the level, 0 is the omega for the beta, and 1 is the omega for change of growth gamma. Note that These values, especially the 5 and the 10 here, are set quite arbitrarily. You can try to estimate it using MLE, and I made a video of that, using MLE to estimate the variances. I just want to set these values to be larger than 0 so that the level and the growth and the change of growth doesn't follow completely or doesn't rely completely on the previous values, but it has some variances. Next, after building the model, we filter. Filter is the process of fitting the model. Filtering is the process of updating our belief of the values, whether it's variances, the state vectors, the adaptive coefficients, and so on. The input for the DLM filter function is the Y10. Y10, if you notice in the previous part, Y10 is a special variable that I make to store the time series of 10-year treasury. Okay, so the first argument is the time series itself, and the second one is the model object. So let's run this. Oh yeah, by the way, I need to show you what the model poly is. So it is consistent with the theory. F here is the F in the theoretical part earlier. And F is a vector of length 3. Well, in this case, it is a matrix of 1 row and 3 columns. The first element is 1 and the others are 0. And then V is just like I said, to be 5. And then this is G. And then W, you can see that the diagonal are matching the W here. And so does the M0. Now let's do the filtering. The DLM filter will output some factors and some matrices. And now let's plot it. The output of the model that we want to look at now is the filtered level and the one step ahead forecast. So we can see here the gray dots are the data. I need to enlarge it, so yeah, if you can see the gray dots are the data, while the yellow line, okay, so now we only see the filtered level. We can see that the filtered level adapts to the data quite well. It can follow the dots quite quickly, like this. And now when we show the one step ahead forecast, it has some errors. Maybe I need to zoom in again. And it still looks that it can follow the data. It can adapt the data quite quickly. So that was the visualization of the outputs of filtering. Now we want to measure the performance quantitatively. We have two ways, we have two metrics to measure the model performance. So the first one is here. It's the mean absolute error. And the second one is the SMAPE. SMAPE is a user function that I defined before. Okay, now let's run this. We see that the MAE is 0.053 and the SMAPE is 2.92. This is quite low. Well, before making this video, I've tried numerous models, and yeah, so I know that this model is on this model's error is on the lower range. Now we want to take the standardized innovation or standardized one step ahead forecast errors by taking the residuals of the filtered model. and I store it in the rest poly. Now earlier, I already said that the errors are assumed to be Gaussian, normally distributed. And so we need to confirm it. And there are several ways to confirm it. I'm going to show you 3. The first one is the ACF. Okay, maybe now you're saying that ACF is for looking and deciding the order of MA and AR model. Well, the autocorrelation, let me just run this first. Okay, so here's the ACF plot of the residual of the polynomial model. And ACF, well, we denote the ACF as rho if rho at time or at like k is 0, it is approximately normal. And so we can see only a few ACF values that are outside the lines. So I think we're quite okay. After all, here at leg 2, the ACF is a little bit more than minus 0.2, meaning that the error at leg 3 is correlated only around 20 or maybe a little bit more than that, negatively correlated with a correlation value of around 20%. So it's not that much, in my opinion. That's why I think if we want to measure the normality, it's still okay. And as I said earlier, the ACF and PACF plots could be used to determine the ARMA model. So here's the ACF and PACF plots for the residual of polynomial model. And judging from these plots, we can say that the plot is in MA process. And MA process is the stationary process, so therefore we can conclude that it seems that the error is independent. Now moving on to the next test is the Shapiro test. Shapiro test is like a formal test, and its null hypothesis is that the time series, which is in this case is the polynomial model residual, is coming out from a normal distribution. The null hypothesis is like that, but we have a p-value that is near 0. So judging from this test, we can reject the null hypothesis. However, there's a caveat here. The Shapiro test has sort of like an effect size. So even if we have only one data point that is straying from the normal distribution, the Shapiro test would conclude that the whole sequence is not from a normal distribution. Therefore, we still need a visual inspection, and we're using QQ norm for it. QQ line here is to draw this line, to draw the normal distribution line. And now we can see that only at both ends that is straying from the line. But it's not very far. It's starting only at around the second quantile. So perhaps it has a fat tails. I'd say that the errors are not very far from the normal distribution. Okay, now I want to show you again the ACF. This means that we have a variance that has not been explained by the polynomial model. So this is why I tried to include an ARMA model, a moving average model to be exact, because as I said earlier, the error is in moving average process. And since we have around 5 that ACF values are outside the line, so maybe it's of a moving average of order 5. There's no unique representation for this, however. Now recall that ARMA model has its own coefficients, both for the autoregressive and the moving average. And now we need to estimate them. We are doing the moving average models only, so the order here is that only for the moving average model. Since we want to estimate the moving average coefficients for the residuals, that's why I inputted the rest poly. ARMA is the function to estimate the MA coefficients. And since the coefficients is stored in the element called coef, I'm just calling this like this to get the coefficients right away and store it in a variable called MA coef. Now I want to build upon the first model, so the polynomial only model, and add the moving average model. The moving average and the autoregressive model is implemented using the same function, which is DLM mod ARMA. So if you want to build an AR model, you would include the AR argument. But since we are only considering the MA part, so yeah, the only argument that I'm going to set is the MA coefficients. We can do it like this. So this is called the principle of superposition. We are just concatenating the vectors, adding or like making the matrices bigger. So we have blocks of each component in the bigger matrix. So the bigger matrix will include blocks of smaller models component. In DLM, we have the word linear in DLM. And this is why we call it linear, because we can add each component of the model in a linear fashion. Okay, this is building the model. And then this is filtering. And now let's see how it looks like. I don't know why my code is acting weird like this. Okay, so this is the data. Let's look at the filtered level first. So looking at a glance, we can see that it looks okay, very decent. Maybe we want to enlarge it here. There's a big jump here in March 9th to March 10th. But the filtered level can still following it well. Now let's look at the one step ahead forecast though. Can the one step ahead forecast do well too? Of course there are some errors, but not too much. Now we'll see how the model performs quantitatively using MAE and SMAPE. Both the MAE and SMAPE are reduced. So we can say that adding a new component, which is the moving average, can reduce the errors. Even though the difference are not too much, the errors are decreasing. So it's a good news. Okay, let's move on and confirm the normality of the errors. Again, I already take the residuals, and then here's the ACF plot. We can still see a variation though. We can still see some ACF are out of the lines. And the Shapiro test also has the same conclusion that the errors are not from a normal distribution. But then again, if you look at the QQ norm, the left tail here seems like, well, I think it's different, no? Anyway, it seems like it has a fat tail again, and only at the very end that it strays from the normal distribution. So maybe we're not that far from a normal distribution. The conclusion is the same. Here, I add the seasonal component just for, well, I just want to see how it goes, because when we see the ACF plot of the second and the first model that we've tried, we see a sine function that is decaying over time. And it looks like at some points, the ACF values falls outside the line. So I thought maybe the seasonal component is the one that could explain this variation. That's what I thought at first, but I want to show you that it only makes the model performance worse. And here I'm using DLM mod Cs to capture the free-form seasonal component. I'm using a free-form seasonal component here because it seems like, well, judging from the ACF plots, the periods, the lags when the ACF is outside the line is not really in a predictable pattern, you know? Like, it's not like every 5 lags, not every 10 lags. And we have like around 3 areas here where the ACF falls out of the line. So I set the season to be 3. It's kind of arbitrary, I know. Maybe that's why the model is worse in some sense. And for the seasonal model, we have only 2-dimensional matrix, both for the W, for the G as well. So that's why we have 2 elements for the diagonal of matrix W. And then this is for the filtering again. And let's plot it. Looking at a glance, it seems alright. However, if we take the measurement quantitatively, we can see that both the MAE and the SMAPE increases after adding the seasonal model. And if you check the residual as well, here we can see that the ACF plots, it resembles more like a sine wave or like a cosine wave than the ACF from the previous models. But regardless of the ACF, we can still conclude that it is independent. The error is independent of time. The Shapiro test also has the same conclusion. The QQ norm, it looks a little bit different now because the sample quantiles, the lowest sample quantiles now is minus 0.04. That is the lowest. And we have more data points that are astraying from the normal distribution. Okay, to get a better idea of how the one-step ahead forecasts compare to each other, I make this code. Again, the gray dots are the raw data. And then the yellow line is the one-step ahead forecast for the polynomial model only. And, well, you can read the legend here. Like this. Maybe I should show all the 3. If you run this, by the way, I will put the code that I presented here in my GitHub. If you download it and run it in your local machine, you will see that the polynomial and MA models generates really similar one-step ahead forecasts. Maybe I should enlarge it here since this is where the pandemic starts, so we had a sudden change. Well, I guess you cannot see the yellow line now. I need to zoom it further up. Okay, I hope you can see it now. So you can see that the yellow line and the green line are really similar to each other. They're really close to each other. but the red line, which is from the third model, is behaving differently. So for example, like in this case, this is the data at February 14th, which is 1.59, and the next working day, February 19th, the bond yield dropped a little bit to 1.56. The first two models, the polynomial only and polynomial and MA, can predict it. So the one step ahead forecast had a decreasing to around 1.58, even though it still have an error, but at least the forecasted value decreased quite a lot. But with the third model, in the red line here, you can see that the one step ahead forecast didn't decrease as sharp as the other models. Maybe this is why the error for the third model is the largest among these three models. Okay, so that's it for today's video. I hope you enjoy watching it and learn a lot. I really learned a lot from this project. Yeah, thanks so much for watching. Please consider subscribing, and I'll see you next time. Bye-bye.